Okay, hi everyone. Thank you for your interest in my presentation about SciKit-GStat, a Python package that can be used to do some geostatistical analysis. If you follow the link from the presentation material, you will end up on this site, hopefully. It's a small application that deploys some content to GitHub pages, maybe you know it. Here on the landing page, you find some useful links, like you find the actual SciKit-GStat GitHub repository here on this link. You find the documentation here on this link. There's also a link to the EGU2020 Sharing Geoscience online webpage. And up here, you can see that SciKit-GStat is also available on Zenodo, so you can actually cite it. It has a DOI. You can launch it on Binder. I will show that later on as well. And there it's on the Python package index. You have the link here. They can click on these badges. And here again is the link to the actual GitHub repository of SciKit-GStat. So what you can do on this page here is I have clicked together a little showcase presentation on how SciKit-GStat can be used. And it's available as a Jupyter notebook that's can also be launched on Binder here following this link. You have to be a little bit patient. It takes a few moments until it starts. You can view an HTML version of this notebook here, so you can't change the code or something, but look into it. And then some of that content that's presented here is also available as a little slideshow here on the presentation. Click on that, takes a moment, and then you end up in this presentation. And I will quickly go through this with you together. So SciKit-GStat is a SciPy, I call it SciPy flavored geostatistical toolbox written in Python. So I tried to stick to the different data types that are available within the SciPy framework. So mainly the NumPy arrays for organizing the data, and you can use pandas to open the data, and you can also convert, after you're finished with the analysis using SciKit-GStat, you can convert the model data into a data frame. So this is just like a short getting started for this year's EGU. I will quickly show you how you can do a variogram, how you can calculate a variogram, and how you can use this variogram in kriging. So this is already the main objective of SciKit-GStat, is to do these two steps. So I have a little file in there as well. You can see it in the repository. You can find it under the Binder link. Or if you open the notebook, you will see how I opened that file. And these are just a sample from an artificial random field that has various observations here. And as you can see, these values range between -3 point something and 1 point something. And it's already quite obvious that there is a spatial structure in this data, as you can see from the colors. You can also zoom in here, inspect the numbers. Yeah, this is what we're going to work with in this presentation. So the main idea behind SciKit-GStat is that there is a class called variogram, and you basically just have to give your coordinates and the data. The coordinates can be n-dimensional, so it's even possible with one-dimensional data. but I have to admit that I haven't tested that so much if everything is really working fine. So usually you would take 2-dimensional coordinates, and they can be 3-dimensional, they can be 5-dimensional, whatever that might be or mean, and you put in the values, so the observation values. And all the other stuff that can be set, that can be specified, is predefined. So you can change it, but if you should change it. But if you just want to try out the class, the package, you can just go ahead. And then I have a lot of methods and functions that will, for example, here plot the variogram so you can see how it looks like. There is a function called describe, very similar to the pandas data frame function, which will return the fitted variogram parameter, like the effective range, the CIL, and so on. Yeah, and that's how it works. So one very short, quick example. So in the notebook, you will see that there is a pandas data frame called data, which has just 3 columns, X, Y, Z. SKG is the SciKit-GStat package, which is called SciKit-GStat in Python. Here you have the variogram object, just put in 2-dimensional X and Y coordinates, and as values the Z column. Then I plot and I plot and describe the variogram. So you can see I'm using a spherical function, a Matterhorn estimator. The effective range is 45.9 something. The CIL, I didn't set up a nugget, and you get this nice plot with the blue points are the experimental variogram. The green line is the fitted model to it. You again see the estimator that's being used here, and in the top section you have a little histogram, so how many point pairs were formed in each of these lags or these lag classes. And you can see that there are only very few observations in the few last lags. That's why usually we would want to limit the extent of the variogram. So how far are 2 points allowed to be separated to still form a point pair? And the variogram has the max lag parameter, which is quite flexible. You have 3 possibilities to put in something. So the default is a none, so there is no max lag, but if you want to set one, you can choose a value between 0 and 1, and this will take the relative share of the maximum distance that's available. So if, let's say, the maximum distance that can be found between any point pair is, let's say, 100, and you said 0.5, then the max lag would be 50. And if you said 0.3, it will be 30, of course. If you choose to use a value larger than 1, it will be interpreted as an absolute value. So if you put in 76.67, that will be the maximum lag distance. But you can also put in strings. Right now there are 2 supported, mean or median, and here the class will calculate the mean or the median value of all pairwise distances that are available. And therefore you have to be careful because 0.5 and median is not the same. 0.5 is not the median of all distances, it's half the maximum distance. So for example, here I'm using this median, can just use the object I used before. I can just change a parameter, plot and describe, and you can see how, for example, the range changed. You can see the histogram, of course, changed because here the x-axis changed as well. Kriging class is quite it's quite easy to use. So SciKit-GStat has only one class for Kriging called ordinary Kriging. If you need to use any other kind of Kriging, there is an excellent package available in Python called PyKrig, and SciKit-GStat has also an interface function to PyKrig. So you can use PyKrig Kriging together with SciKit-GStat. That's possible, but I will not focus on this. And basically, what you do is you pass a fitted variogram to ordinary Kriging, and then you can use the transform method to transform any coordinates that you just pass on to ordinary Kriging to get a prediction. That's the basic idea. I decided to always force the user to do these two steps. So I'd first create the variogram and then the Kriging, not do that automatically, because I think it's quite important that you see the variogram beforehand and that you're sure that you can use this variogram for Kriging. So this is how it works. Up here, I'm just creating a mesh grid, just X and Y coordinates from 0 to 100, because this is the extent of the original field, 50 in each direction. I'm building the ordinary Kriging class here. This is our variogram object. And then I transform these. So the ordinary Kriging class needs one-dimensional array for each available dimension. We're using 2D, and I would suggest only using 2D because technically it can handle more coordinate dimension, but I haven't tested that so far. There was no time for that. I still have to do that. And then this is the result. So you can see our observations here, the black points, and the prediction in the background. So we can again zoom in somewhere, like maybe here. You can see here, for example, the Kriging predicted -2.5, and the observation very close here was -2.7. So that's fair enough. Here we have 0.4. And the prediction next, the cell next to it is 0.37, 0.47, 0.55. So that's quite nice. One of the main features of SciKit-GStat is the theoretical model fitting. So there are a lot of other online resources. So in the documentation, you will find a tutorial dedicated only to theoretical functions, one tutorial only dedicated to semi-variance estimators. There are different available in SciKit-GStat, and you will find what I call the technical note about the fitting procedure. So I have prepared a whole notebook just focusing on how does the variogram class implement the fitting, and where can you as a user or maybe a future developer, where can you opt in and change the behavior. So what you can do to change how the variogram is fitting a function to the experimental data, you saw before that it is doing that automatically. There are different possibilities. First of all, you have estimator, so variogram point estimator. That's a property where you can set the estimator that you want to use, for example, Maturon or Cressy-Hawkins. The same for the model, so the theoretical variogram model function that you want to use, like a spherical model or a cubic model or whatsoever. And this should be a point here. Then there's variogram point fit method, where you can change the fitting method. At the moment, there are only two available, two different kinds of least squares. but I'm planning to implement the maximum likelihood method as well somewhere in the future. And then we have one other property called fit sigma, where we can weight the experimental values to influence the fitting. So give more weight to, for example, closer points. And all of these properties are implemented in the way that you can pass a string to select a predefined estimator, for example, or model. And for estimator, model, and fit sigma, it's also possible to pass custom functions. So you can write your own model or your own estimator, or directly give the weights, and you can do some weird stuff there. So how does that look like? So the first thing that we can do is we can switch the model to a Gaussian one, because as you can see, that works better. Up here, I'm just creating a two-column figure here, plotting the first one, which is still using the spherical model. And as you can see here, to plot this plotting function, I can also pass a predefined canvas object from Matplotlib here. So where to plot it, not creating a new one, but using an existing one. And I don't want to have the histogram here because I have only two plots. Then I just change the model to Gaussian, gets fitted, and so on and so forth, and plot it in the other plot. And you can see that this model is lining up quite nicely with the first few bins here. We can do the same thing to, for example, use the doubt estimator. There are different available. You find that in the documentation. Basically, we have Maturon, Cressy, Doubt, and Genton. And there's also a possibility to use the Shannon entropy as an estimator. And you can see, you have to look very close. Here we have the Gaussian model with the Maturon, as you can see here. And here we have the Gaussian model with the doubt estimator. And if you look into these larger bins, you will see that the experimental variogram actually looks different. You can also tell from the y-axis. Also, it's quite easy to change that, to plot it and look at it. There's way more. Here's a link to the documentation. I cannot cover everything here, so we can change the fit method. Basically, we have Levenberg, Marquardt, and trust region reflective as least square methods. One is more robust, the other one is faster. And here's just one picture from the documentation. I just took it out of the documentation where you can see the different fitting methods in the different fit sigma methods in action. So here you can see that the same variogram model, which is in all cases a spherical one, gets fitted to the same experimental data, but using a function to calculate weights for the different experimental values, mainly influenced by the distance. So the closer an experimental value is, the more it gets weighted. And the function that is used, shown here, so just the black one, for example, it just decreases the weight linearly with distance. And square root takes the square root. So you can see that the result is quite different. You will find more in the documentation. And that's already it. That's my showcase. And I have a few final words. Of course, there's way more. You can check out the GitHub repository. You can check out the documentation. And there are also more things to happen. So for example, there's another way bigger framework called GStat framework, They have way more than just variogram analysis, which is my and SciKit-GStat's main focus. And we're in contact, so maybe we will join forces, and maybe SciKit-GStat will become a part of that framework to have all geostatistical relevant Python packages in one framework. And these guys also have a display in the very same session on the EGU, so please also check out their presentation. I think it's really interesting what they do. And yeah, and what I will do during the next few days is I will add another presentation and another notebook up here to talk a little bit about the interfaces to other libraries that are part of SciKit-GStat. And basically that's it. So what I wanted to show you before, just that you see this here, this binder link, you can click it and you will be redirected to binder, and here you can start the repository. It might take a few minutes, so we have to wait, and you end up in the notebook here, up here. And here you can run that. So for example, if we run that line, and you can see there's more. Takes a moment, it's slow because this is running as an online version. Here we can, for example, just change the code and look into tail, see other values, or I don't know, use the describe function. That's quite cool. So you can also use this notebook, and yeah, here you have to rerun the interactive plots there. It's all there. You see, I put some of the documentation into there as well. So please also check out that notebook, and you can use it online. So you don't have to install anything. You can try around, maybe even you could also upload your own data there and directly use it here, and so on. So that's it. Thank you for watching, and I hope we see each other in person on the EGU 2021 then. Bye-bye.